Well, we're ready for a new chapter. Now we're going to start looking at chapter 10. And chapter 10 in Pinter's book deals with the concept of order, in particular, order for group elements. So we've encountered this concept a couple of times now, but I think we should probably give a precise definition. All good math talks start with a definition. So for us, the definition of order is as follows. The order of G in G is the smallest number n, natural number n, such that G to the n equals E. And a couple of remarks about this. First is we do not allow 0 in n for the purposes of this definition. I know some people have very strong feelings about that, and I don't want to imply that there's a right or wrong answer, and I don't really care. But the point is, if I don't specifically remove 0 for the purposes of this definition, then we're in trouble because every element has G to the 0 equals the neutral element, kind of by definition. Although we should talk a little bit more about exponential notation in just a second. We accept this as a convenient way to make this make sense. If there is no such number, that's a possibility. Then we say G has infinite order. And whenever we're talking about order, we've been using absolute value bars. So we could say that the order of little g is infinity. Now, I'm using this exponential notation because, as before, we are always saying that we're using multiplicative notation for groups. But just as a reminder, there's no reason why, once we're using multiplicative notation, that we can't use exponential notation to refer to repeated multiplication. And if we do that, then we're happy because all the familiar exponent rules, sorry, the mouse is a little bit unhappy, familiar exponent rules still work. So for example, I think there are essentially 3 of these. The first one says that exponents add up. The second one says a power of a power multiplies. And the third one says that negative exponents are essentially the same thing as reciprocals. And I guess if I'm really being clear and rigorous, I can probably prove this one from the other two. This probably doesn't need to be here, but it's fine. There's no rule that says I have to be as efficient as humanly possible. I don't want to prove this in great detail. Let me just talk about this one for a second, just to give you the flavor of what's going on here. What this is saying is I have a group of m copies of A being combined under whatever the group operation is. And then I want to take the result of that and do that n times. Well, the usual way that we understand that is when we're doing multiplication, you have A m's being multiplied, and then you have n groups of that. It's the exact same logic, right? Except the only difference is that the multiplication here might not mean, normal number multiplication. It might mean group element multiplication. But who cares? The reality is it's a group of m, and then I have n groups of those. How many of them in total are there? M times n, where that is the usual multiplication. It's just, a to the mn power might mean something different. Okay, so what we're going to do with the remainder of our time in this video is discuss basically what order means in a group element, for group elements. And in particular, we're going to prove the following little theorem. If G has order n, now n is possibly infinity, then there are exactly n distinct powers of G in G. In other words, if n is a finite number, then g to the 1, g squared, g cubed, and so on, those are all exactly distinct. And if n has infinite order, then all of the different powers of g are distinct. And the proof of this is not very difficult, although we do need to distinguish between the two cases. So the finite case and the infinite case, which we'll treat separately. And main idea is the division algorithm. So let me remind us how that works. The division algorithm says if you have two integers, maybe I should write given n and d, with d less than n, there are integers q and r with n equals qd plus r, and 0 is lesser or equal to r is less than d. Okay, so this might seem a little bit cryptic if it's been a little while since you've thought about this, but it's actually incredibly straightforward, right? Q is the quotient and R is the remainder. So all I'm saying is do the division like normal, but instead of getting a fraction, right, we remember from being little kids, not dealing with like decimal points or fractions or whatever, having a remainder in our division. And that's all this is saying, that if d is a number less than n, I can do n over d, and I'll get some quotient and remainder back. Okay, so first step is to look at the finite case. Let's say now that g has order n. I know that's a little bit, okay, maybe we should, what's the right notation here? I'm a little bit worried because I want to do division, but I just use this letter n like here. Okay, let's say g has order d. Which is a finite number. Then, given any g to the n power, I can do the division that we just prescribed. Right? I can write n as qd plus r. But now, since we know how exponents work, I can write this as g to the d to the q power times g to the r. And because g has order d, g to the d power is the neutral element. And the neutral element raised to any power is just itself. So this is just a complicated way of saying g to the r. So in other words, if g has order d, I have a little bit of an upshot here. How do I say this? We can simply reduce n mod d, and the equivalence class, which is the remainder, tells you which power of g that you get. So in other words, the z mod nz's that we've used as occasional examples are kind of fundamental for thinking about group theory, because in some sense, every group operation, every group element and its order can be thought of in terms of this just z mod nz, or in this case, z mod dz type stuff, right? You just reduce this mod d and then you know which element you're looking at. So we know then that we can look at the powers from 1 to d, or 0 to d minus 1. It remains to prove that they're different. And for this, we do a little proof by contradiction. So assume that we have, let's see, what letters should we use that we haven't used already? How about just A and B? And these are guys are less than D because, those are the ones we know that these are distinct. So we have we need to prove that these are distinct. So we have two things that we want to show are distinct, and we assume that we have them and that they're equal. Right? So we have two powers which give the same thing. Now, of course, if A and B are already equal, then this is not going to be any kind of contradiction. So we should also assume A is not equal to B. And therefore, one of A and B is bigger. So how about we assume that A is more than B? This is what we call without loss of generality. In other words, if it was the other way around, I would switch the notation, but it wouldn't change the argument. So therefore, if A is greater than B, then what that means is I can multiply both sides of these by g to the minus b. That gets me to the identity over here. And because of our exponent rules, g to the a minus b over here. And now we're ready for the contradiction, because if a is greater than b, a minus b is greater than 0, but also less than d. And the contradiction is that d is supposed to be smallest possible element such that g to the, that power is the identity. And so this can't happen. This is a contradiction. So therefore, this isn't true, and all powers are in fact distinct. Okay, so this handles the finite case. We have not yet dealt with the infinite case. And so let's turn to that. And here we have done pretty much all of the hard work already, because in the infinite case, what I'm claiming is there is no power of g which can ever get you back to the identity element. And so, in other words, what I'm saying is all the powers of g have to be distinct, is essentially the only thing there has to prove, right? Well, what to say? In essence, we already did this, right? We kind of just did this. Apply the previous logic. Here, it's very similar. The only difference is I will not have this assumption anymore, right? Because there is no finite element, there's no finite order D. So this part's not true. But if I had two elements that are ever equal, this part would be true. So we conclude that there would be some power, which, not 0, but E, right? But we said G has infinite order. And so we once again reach a contradiction, because this should never happen. All right, I think that kind of takes care of it. And so this was a really quick crash course in chapter 10. And so rather than break up chapter 10 and then do a bunch of problems and so on, we're going to follow this up with a real quick chapter 11, kind of back to back. And then we will be, ready for our midterm exam. I know it feels like it came up real quick.